Okay, you may start now.
Okay, thank you for opening the session. So we'll start with the the next session, and I welcome everybody in this afternoon. So we stop here because as we have introduced the FG-based combustion model, it was introduced in the turbulence combustion session. So we have to solve two main equations. So in addition to their continuity equation and their Navier-Stokes equation, we include the mixture fraction equation and the progress variable. And these allow us to generate this kind of table. And I show you how we will generate from the turbulent chemistry to reduce it, and how we will use the presumed PDF to get the lookup table, and which is now in interaction with LES solver. The LES will provide a set of quantities, so the mixture fraction, the variance, and the progress variable. And here we will get everything tabulated, and we will get the new values and of these different parameters. We know it should be the density, the viscosity, temperature, and etc. And we have this loop to account for the chemistry turbulence interaction. So let me now make summary of what I said. So here we have the PDF. One way to get this PDF is to presume, and that is what I summarize here. So we have the chemistry and the flow, and these interact by means of this PDF, which can be presumed, but we can also solve a transported equation for this PDF. We know that for the flow field, we will get the velocity field, the mixture fraction, and also the progress variable. And these will, through consideration of presumed monad, we'll go to the chemistry and we'll get this quantity. And from presume or from the transported PDF, we'll obtain this value which come back, and we have this interaction. So once we presume the PDF, we have a restrictive assumption because we say that the interaction is reduced only to what the presumed PDF allows. This means that we do not consider the physical process taking place in details, and also we have not a closed chemistry source term. First, we have this, and the chemistry will be from the detailed chemistry, we will reduce it and in a tabulated way. And by presuming, as I said, we have this restriction. And if we transport the PDF, we remove this weakness of the presumed PDF, and we solve the transport equation, and we get from these the chemical source term in a closed form. And then we can couple this, but the solution of this can be made by Lagrangian formulation or Eulerian one. Here I will show you how the Eulerian PDF can be solved, and it is what we use. Is it what I use normally? And I will also show you some examples. This Eulerian framework is based on the Eulerian stochastic field method. So we have naturally the PDF, the FGM, but we use also the flamelet progress variable tabulated chemistry, and we compare both the Presium PDF and also the Eulerian. Naturally, for that, we have to solve, if we use the Eulerian PDF, we solve this equation, and this equation, the transported PDF you have learned in the turbulent combustion part by Professor Schocker. So using some, you have learned that solving this equation is very, very time consuming. That is why there is these two ways, is following the Lagrangian form or the Eulerian framework. And if we use the Eulerian framework as we do here, we have to solve n stochastic field, for example, and this transported equation can be transformed in this form where we follow only now the stochastic field, the n stochastic field for example, the mixture fraction and for the progress variable. In this equation, so clearly, so we have the accumulation part, we have the macro mixing, we have the chemical source term, we have diffusion transport equation in which we did an assumption here. We say that it is a gradient assumption for the diffusion, and we have the micro mixing. I think Professor Schocker showed you different models used to describe this micro mixing. And transforming this, we obtain exactly what we have, and the Wiener term take into account these different fluctuations we could not capture without introducing it. For this Eulerian stochastic field, we have to solve the set of equations. We have the continuity, we have Navier-Stokes equation, and we have these two set of equations for the mixture fraction and the progress variable. And we need a number of stochastic fields, and we will see the effect of this stochastic field on the results. It depends on configurations and on situations. So we'll show you some results for this single phase combustion, the turbulent combustion phase. If we have this stochastic field, then we can obtain now the mean value of the filtered the mean, the ensemble averaging through this n number of stochastic fields. So this was for this first part. I would like to complete it now, and it is completed now. And let me now show you or go into details of this Eulerian Lagrangian methodology for describing turbulent dispersed spray combustion. I will give some runs results and LES mainly, and the turbulence modulation. So we'll take what we introduced in the previous part, where we account for the turbulence modulation modeling. And naturally, we use this equation for the Lagrangian tracking, in which we consider turbulent dispersion, the phase changes, and now we include the combustion. That is why we have introduced this equation before, so that we have to put this element together to account for the interaction between these different processes. We will show also how we will couple the spray with the carrier phase and some experiment. That is exactly what I would like to say. that we will now couple the modeling we have provided or we have designed to account for the chemistry turbulence, to account for the turbulence. So I think you have also learned different LES models, starting for Smart-Borinsky, one equation model, and whale model, sigma model, etc. And here we have put different models here. The primary breakup is not considered, but we will consider it tomorrow when we will introduce the coupling of Wolf and Lagrangian. So I have shown you only one result with the volume of fluid method, which allow us to capture the breakup, the primary breakup. You can also follow the calculation to predict the secondary breakup. And for the two-phase flow, we introduce everything which was needed, the mixing, the heat transfer, the mass transfer, and also we will now introduce the chemical reaction. So we focus now on this here. This was shown also yesterday. I recall something which is the reduction from the detailed chemistry to reduce and to make it available for the LES or RANS calculation with the lookup table based on FGM or on the flamelet progress variable tabulation. I refresh you with what we have introduced, these two ways to calculate to a model spray, either to use the Eulerian Lagrangian, in which we track the droplets through the flow along its trajectory. And here we have to solve the position, the motion equation, in which we need different forces we have introduced. And normally, in many applications, we have this assumption which allow us to account only for the drag force and for the gravitation force. And here the Eulerian, so as we've seen, we have learned, so we consider this two-phase as continuous phase, and they interact, and the modeling here is very high, as I try here to point out. So for the Eulerian, the advantages and disadvantages of the Eulerian Lagrangian. So in the Eulerian, we know Eulerian Lagrangian, the fluid flow is treated as a continuum. So the Carrier phase is described following the Eulerian description. That is why it is called Eulerian. The trajectory of a large number of particles can be droplets, can be solid particle, bubbles. It is tracked throughout the flow field. We base on the force balance on each particle. This is what we have introduced yesterday, the BBO equation. So the dispersed phase is tracked by Lagrangian tracking, and there we call it, that is why we call it Eulerian. So the modeling of the phase change of the collision of the wall interaction, it is physically concrete and clear because we follow the trajectory of our particle. We know where it is, and if it interacts with the wall, we know this. If there is collision, we can clearly follow the process. Because we have a large number of particles, so we need to carry out a statistical mean value to obtain statistical mean values of the dispersed phase. And for that, we replace the real particle by so-called parcels. And these parcels are the computation parcels which have the same property, which which represent a large number of real particles with the same properties, at least with the same velocity. And not only also we can say the same properties in general. This approach is appropriate to flow where the dispersed phase has low volume fraction and does not significantly influence the flow behavior of the continuous phase. It can, and in this, if it is so, we have the two-way coupling. And if we have the two-way coupling, then we have to account also for the modulation modeling. And here we know a little bit what this means. It is about 10 exponent minus 3 if we are in this domain. For example, lower than this, then we can really use this approach. If it is high, then we have to include the interaction between particles, then we have collision, we have the four-way coupling, and we need appropriate models for collision. I have introduced these also, these different collision models we can found, and I have also shown how we improve this kind of consideration. If we compare the Lagrangian and the Eulerian methods, so the stochastic Lagrangian method and the Eulerian method in which also the particulate phase is described by Eulerian method, we see that this is robust and accurate as we can follow the process along the trajectory of the particle and by also monitoring its influence on the particle and is the feedback of the particle on this flow field. It is well established and widely used in the industry, and this can be found in many CFD, industrial CFD code. But we need a large number, sufficient amount of simulated particles, the so-called parcels, in order to avoid statistical noise. The computational costs strongly depend on the unsteadiness of the flow and the mass loading of the system. If it is very large, we can also add some collision. We can have some collision effect, and we have to account for. It is challenging to achieve an optimal parallelization of the solver, but this is now improved, and we have the fast coupling. It is not straightforward, but it is made. I show you one diagram in which we have seen how the source term has to be calculated, and if the source term is very large, then we have to introduce some under relaxation parameters to make it stable and to go to convergent solutions. Eulerian methods. So computation cost does not depend on this here, because the set of equations we will get here, it is exactly the same as we have for the Carrier phase. So the solving procedure will be the same, and the equation of both continuous dispersed phase is they share the same structure, but we have yet to introduce a lot of models, and but the phase coupling is straightforward because we have the same structure. It is not a problem, and we can also realize an optimal parallelization. We did it, but it is not exactly what this theory said. Yeah, we obtain the computation cost was a little bit higher here if we compare to stochastic Lagrangian method, but it depends on the number of sizes. And this one allow us to capture in a easier way the polydispersity. And this one can allow this, and I will show you that the classical Eulerian cannot do it, but we introduce some improvement in the, it is done in the literature now, and we have the so-called multi-fluid method, which allow to get the polydispersity, but it is still limited. We have naturally the way to do it using the transported PDF, and it is what we are also trying to do. And we can also have a coupling of Eulerian and stochastic field. That is when we will try to propose, we are trying now, and in the literature, one can find the coupling, for example, of VAF, volume of fluid method, and Lagrangian, in which we have this coupling allowing to account for the primary breakup and also for the secondary breakup and fit to the Lagrangian one. But there are also methods which allow, make it possible to get the droplet size distribution at a given distance from the nozzle and to prescribe this and to give this to the Lagrangian. There is also other models like this momentum model. It is still not mature and it is still used for academic application, but some people try to extend it, limit it. The limitation is on the number of particle size you have to use. So now we will apply these two to our turbulent spray combustion, and we'll start with the Eulerian Lagrangian methods. We have our set of models. We have the description of the Fourier phase and the description of the Lagrangian phase. Here we have the classical generic transport equation. As we have seen before, we have the source term due to non-convective diffusion. We have the source term due to the presence of particles without changing phase. Here we have the source term which account for the phase change, and we have the source term due to combustion. I have shown you some results, but I did not go into details on this. Now, if we use the tabulated chemistry, we know why it is important now from your lecture yesterday on turbulent combustion. And if by doing this, we assume that we are dealing with presumed PDF, then we have to add the transport equation for the variance. We have for the mixture fraction, this mixture fraction, sometimes I call it F, sometimes I call it Z. Yeah, in Germany, so we call Z and F. It depends if we are thinking in English or in German. And we have the transport equation for the progress variable. Then I have told you that in this case, the mixture fraction is no more a conservative quantity. For singlet phase combustion, it is a conservative quantity, but not for two-phase flow. And in this equation of variance, we have an additional term which account for the phase change. And this was given by this expression as I studied. So this is the set of equation we have to solve. From here, we'll have the continuity equation and the momentum equation. And then we have this set of additional equations. We have also, here we have, excuse me, we can also have the enthalpy equation if we deal with, for example, this premix. So we have now the transport equation, what we have to solve for the motion of our droplets with appropriate forces. We have this equation for the variation of mass of particle, and I summarize everything here as we have seen yesterday. And this equation also we have introduced it yesterday. So for the Lagrangian part and for the Taylorian. If we assume, as we said here, we assume that we have a presumed PDF, so that we have this modeling of variance. And we account then the chemistry turbulence interaction by means of this presumed PDF. And we have explained all these things previously. Using this presumed PDF assumption, we have tried to carry out some reacting jet spray cases, and we have used the so-called Sydney burner. It is this burner here. It is stabilized by annular pilot flames. These pilot flames here, almost, I think they are, yes, we have 72 holes. We have also the co-flow, and it is provided, so this flame arc can be seen here. We have also the co-flow within a diameter of 104 millimeter. So with this, the question is, which kind of spray, which kind of combustion mode we will have? Normally, in spray, we normally have either partially premixed combustion or mixed mode. Because while premixing is occurring with the Carrier phase and surrounding air, the fresh fuel is continuously supplied from the evaporating spray and changing the local stoichiometry. This means that we have to deal with partially premixed combustion. We can also have some mixing mode within, but it is not really easier to get premix combustion for spray, but this can be done if we assume that everything is totally evaporated before combustion, before entering in the combustion chamber. It is such kind of pre-evaporated system. So mastery in Sydney, they carry out different experiments for different fuels. Was for acetone. They didn't also for ethanol. And they have a set of ethanol flames, ethanol 3, 6, and 8, with the difference of the jet velocity. And these imply also modification of the mass flow rate and of the Reynolds number. This is the numerical setup. So here we have the fuel, which is coming here, and here the air, and the outside is there. And this is our computation domain we have used. We use this quantity as inlet temperature, and the turbulent intensity was 5%, and the grade is so much, and the droplet number of the number of parcels was 1 million, and we provide result at these different axial positions. We have here from 0.3 to 30 diameter. The first was to capture the diameter distribution, and I put now a volume flux to make it clear with what we have discussed yesterday. It is normally the flux of the particles, but people would like to call it volume flux because it is seen during during a specific time, for example, 1 second, 1 hour, and so on. So we see the evolution of the particle size, the radial direction, and we have here experimental data, and we have our simulations, and it is the same observation. With experiment, we can also only have access on a very reduced domain of the system, but numerical simulation allow us to get more details. And this is the flux we obtain, and here we have exactly a very good agreement with experiment. In this case, we didn't consider the dispersion model. Why not? We try only to assume, or we have assumed that the turbulent kinetic energy was resolved in a very good amount, more than 80%. As I told you, I think in the morning, if we have these criteria, and this means that the main fluctuation would have effect on the the filtering quantity is considered, and the subgrid scale fluctuation can be subgrid scale dispersion effect can be neglected. So we have now here, this was for ethanol 6, and here now for acetone. Acetone 3, acetone 6, and acetone 8. We see that the results obtained agree very well with the experiment, but at these positions, this year and this, there is some deviations. And at this time, so I sent my collaborator to Sydney to discuss with our colleague in Sydney to understand this deviation. And the outcome was that the exploitation of the numerical data was not correct at this position here. This make now a good assessment that people has to use a numerical simulation, or experimentalists have to use numerical simulation as also a kind of validation for the experiment. Then we have a two-way coupling of validation. We have the validation of numerical simulation using experiment, but we know also that in experiment we have some uncertainties, some errors. That is why the numerical simulation can help also to validate experimental data. This was for the size of particle, and we try to also get the temperature evolution. The temperature evolution has been obtained in this way. And here we see that at the beginning, we have a correct behavior, correct approximation, correct prediction of the temperature with a large deviation here. And then we have this at this point, exactly at this point here. And they show us that there is a problem, and this problem may be due to the fact that we neglect the heat transfer, and our table was an adiabatic table. It is the reason we have to extend the table to non-adiabatic table. And at the moment, we are doing this in the framework of entropy evaluation. It is what I will speak about tomorrow, how we can optimize a spray combustion or combustion systems by using the entropy prediction or by means of exergy analysis. There we will get the distribution, I think, in a correct way. So the next model to account for the interaction between the flow and or the turbulent flow and the chemistry is the artificial thickness flame model, the ATF. And this way to account for the artificially thickness model, this model allow to, or it is a way to avoid the fact that in LES we are not able to resolve the thin flame fronts. And to make it resolvable by LES, the way is to thicken it. And this is what we do here. If we thicken it, we reduce also the wicking. And if we reduce the wicking, then we have also to reintroduce a wicking model to obtain the previous physical properties. We see that for premix and sometimes also for diffusion flame, the thickness of the flame is very thin, 1 millimeter or less. And with LES, it is sometimes difficult to resolve this, also in the premix and in non-premix. So by doing this, what is the question? The question is to introduce a more diffusion process. And if we introduce more diffusion process, then we have the thickened flame. It is a thickening factor multiplied by the diffusion. And for the kinetics, and here for the flow, and also here for the thermal. And if we have this, then we have a new thickness of the flame, and it is what we had before multiplied by this factor. It is the thickness factor. And this factor should play a role also on the chemical reaction. And we have this chemical reaction, it is also modified. And to keep it correct way, we have then to reduce, to divide by F. And if we multiply this or the diffusion by this factor and divide this by this factor, then we keep the flame velocity constant. So the idea is to thicken the flame by preserving the flame velocity. If we do this, then to summarize, if we do this, we say that we thicken the flame, we reduce the wrinkling, then we have to introduce a correction, and this is this correction here, and these allow us to get the previous reality. And in our questions, So we have in this continuity equation, we have the source term. In the motion equation, we have no modification. We have the source term due to this, to the two-phase flow. And for the progress variable, which is affected by this thickening, so we have the thicken factor multiplied by efficiency factor. And also we have to track the flame. And then we introduce the flame sensor. And the source term has to be also modified. The source term of the chemistry. So it is divided by F as we have here, but we must multiply by this to get everything correct with the flame speed. And here, the source term due to evaporation or to other source term, so as to be also taken. So this quantity is the weakling factor, what we have here to get the weakling correct. And typically, the weakling factor was proposed in the literature. The most used one is from Charlotte, and it is given by this here. We have here the flame thickness. We have here our grid, the fluctuation on the grid size, the Reynolds the Reynolds number, and we have here our flame speed, and we call this beta. It is a model parameter. It can be put as constant, but we have also tried to make it a dynamic, and we have some dynamic procedure to calculate this. So for that, to generate this model, we assume the equilibrium switch in the flame and the turbulence, and we try also to include some fractal dimension in which we have this beta, and it is this factor. And we can calculate it by putting a constant value or by following it by using a dynamic procedure, which I will not show here. So using this with Sacomano, so we try to use the RTF model, okay, as we have here, coupled to this, to the Lagrangian part, to track the flame. And this was this configuration from earlier. We have the liquid fuel atomization, and here we have an air-assisted atomizer, and we have the flame, and we have the pilot flame here, and we got the distribution of the droplets at this position. So that is the grade we generate, and we obtain the following results. But the experiment was carried out using different air to fuel ratio, different equivalence ratio, that is 0.72 and 0.79, 0.87, and with these different operating conditions. And what I produce here is the result of, with this equivalence ratio. Here we coupled LES, the RTF with the FGM table, and also we track the droplets by means of the Lagrangian. So we produce a different diameter here, as we have introduced them during the lecture in which we have spoken about the characterization of spray. And we see that the experimental data and numerical simulation agree very well. And this is the question we have used to determine this. That is the D30, D20, and D1 0, and we can put these and see what we get. And we have tried to compare the ISO contour of the mean value of the experimental reaction progress variable on longitudinal plane crossing the axis of the burn. And that is the first part. The first is a contour. This is the second one, and this is the third, three different positions. And we see that we got a very good agreement by using the RTF model. And the radial profile of droplet velocity and volumetric flux so is also very good. For the velocity, we obtain a very good agreement. And for the volumetric flux, or for the mean flux, so we obtain also a very good agreement. So the result lies within this area, within the uncertainty interval, and the two positions are this here, the first one and the second. What was the idea there? The idea was that we put, and this is what also you have to think about. So we put here the correction of the flow, and we change the thickness of the flame by modifying the diffusion parameter, diffusion coefficient. But if we change this, we modify the flame, this means also the time taken by the particle to cross the flame will be changed. This means that we have also to modify this effect here by accounting for the thickness. That is what we did later on, by in which we say that we have to account for the effect of the artificial flame thickening on the dispersed phase. We have normally this equation, but because we have thickened the flame, the particle has more space to travel within the flame, then the temperature of the particle and also the evaporation rate will be different. And that is what we did here. We divide this quantity by the thickening factor, and this quantity also by the same. And we try to see if there is an influence of the thickening on the evolution of the droplets, for example. The first one is this here, in which we try to compare the results from small, if we consider small initial diameter, which is small and which is very high. And for that, we did first without changing the thickening. This is the red one. It is the reference case in which F is equal to 1. And by changing the thickening, we obtain different behavior. This means that this effect is really there. It was published in 2017, the effect of the artificial flame thickening on the dispersed phase. And apply to the same configuration, what we obtain. We obtain these results here for now, this different equivalency ratio. But here we would like to compare what we obtain using the RTF and using the beta PDF. So using the beta PDF, we see that the result, that are experimental results for different isosurfaces. And here we see that we have not a very good agreement at all with this position of the flame. It is the isosurface of the reaction progress variable. And by using the correction, so we see that we have sensitivity, real sensitivity, which goes to the correct direction for this flame here. And for the other flame, we didn't do it with the beta PD. So this means that this effect is already there. And if we would like to get correct results, we have to account for this effect. And here we compare with the experimental data too. So we see that the result is also very, very encouraging. So let's now move from the presumed PDF to the stochastic field where we don't have the presumed assumption. If we don't have the presumed assumption, then we will account for the real physics. So that is what we assume. And I will start with the single phase combustion, and then I will show you how this Lorentz stochastic field method is modified when we account for the presence of spores. So as I introduced it before, we will solve this set of equations, the continuity equation for single phase combustion. We have the momentum equation, and we have this set of equations for the progress variable and for the mixture fraction. And we have these different terms as we have introduced them before. And we try to do it for two types of configurations. We did it with the flame D and with the oxyflame case series by Sevolt in 2020. We did it using RANS and using LES. This is the flame D configuration here, the Sandia flame, and we use then the same, almost the same experimental setup, but now not with flame D, but with oxyflame. So what is the outcome? So the outcome is that we have to see the flame structure, and also we have to see how much, which number of stochastic fields allow us to get the correct result. We see here we have the experiment of the dots, and the experiment, the numerical result using different number of stochastic fields. We see that with 8 stochastic fields already we get the correct. We get, I can say, correct behavior, but we need more, up to 48 if we look here, and 128 provide really the correct behavior everywhere. We can then say that we have a good agreement, good prediction of the flame structure at this different level here for the mixture fraction here, for the variance, for the temperature, and also for the velocity of the flame, of the flow field. Here we use the flamelet progress variable approach in RANS. We did this also with the LES, and with the LES we will see the advantage. And we can start with 48 stochastic fields, and it is a very good compromise between an accurate prediction and computation costs. So if we use LES, we see also the result here for LES, and we see that the LES result with at least 8 stochastic fields allow us to get the correct results if we compare here for the velocity, axial velocity, and here axial velocity and transversal velocity and the temperature, and also for the mixture fraction. And we see this, and we can see the result here with almost 8 stochastic field. We can get the correct prediction if we use LES. And by using LES also, it could be possible to get the scatter plots in which we plot the temperature as function of the mixture fraction in order to see if we have some extensions or not. And this is the case where we got the correct behavior in the, if we use here the experimental, this is the experimental data, excuse me, and here we use our stochastic field, we get almost the same results, and it is very nice. Here we use as a micro mixing model, the interaction by change of mean, which is not local, and we got the very good agreement with experimental data, and using at least 8 stochastic field with with LES. And for these two, we see here also the evolution of the PDF. We'll get the PDF here for different stochastic fields, and for this different position 15D and 30D. So the probability density function has been calculated within a mixture fraction range of 0.1 to get all these results. This is for the single phase combustion, and for the two-phase flow, we see difference of the equations. So the equation we obtain for single phase combustion is this here with this different value we had, the accumulation, the macro mixing, the chemical reaction, and here for the diffusion, and this is for the micro mixing. And if we account for two-phase flow, then we have to take into account the effect of the presence of particle, and especially the presence of the evaporation rate on the distribution of this, on the characteristic of this PDF, and this is this term here. And when we reduce everything to deal with stochastic, Eulerian stochastic field, so we obtain also the same equation, but we have an additional term which account for the effect of droplets. This means that here we have directly the effect of droplets on the chemistry, and that is very interesting because we have also we include indirectly or directly now the effect of the presence of particle, and then we account for the interaction between chemistry and particle. Here we had only the influence of chemistry and turbulence. Here we have the interaction of chemistry, turbulence, and particle. And this paper, we published this result in this paper here. This equation has been introduced the previous time by Jones. We use it for different kind of sprays, and we extend it here by using tabulated chemistry. And the Jones did it without tabulated chemistry, and this is the novelty we have put here in the framework of tabulated chemistry to account for this, and we extend this also. And here I put everything together. Excuse me that it is in German. So we have the stochastic field, which is the central point. We have the Eulerian description, and we have the particle tracking. And the particle tracking provides us the source terms. And these source terms, and from the stochastic PDF, we obtain the filtered parts. We get also from the LES, we get this source term first. We go to the LES, and we obtain the results which come here and go there. And from here, we obtain the result. The result we obtain here went to the kinetic, the tabulated chemistry, and from the tabulated chemistry, we obtain also the filtered quantity. And that is, which is very nice in this way. Here, X is only this, the mixture fraction, the enthalpy, and the mass fraction. We have to extend it to non-adiabatic case. Now we apply this in two-phase flow. Okay, I have shown here how to apply it for single phase, and here we extend it and we apply it for two-phase flow. And for that, we use the same configuration, the Sydney configuration with acetone, with ethanol, but here we have only used the ethanol case, and it is the ethanol 6, the flame 6. This is this one here, and we try now to compare them. This is the piloted parts. We have shown the spray jet, and we have the co-flow. So here we see that we have the temperature here, and here we have the mixture fraction. And at this position, we can show the result we have obtained. And we see here that the calculation allowed to get more details in the physics. And with the Eulerian stochastic field, we use the number of stochastic field 16 to obtain this result here. And we have the flame lengths, we have the correct distribution of the mixture fraction. But at the end, we compare the result we obtained there with what we have obtained with the artificial flame thickness. If we compare for the axial mean velocity, for the RMS, for the radial velocity, and for radial RMS, we see that the stochastic field and the ATF results agree very well. And everywhere, we can say. And if we go to the temperature and the mixture fraction, and we don't have the result for the mixture fraction there, we obtain these results here for the temperature, and we see that the result is exactly the same for both. The RMS is high with the number of stochastic fields. If the number of stochastic field is high, then we have less. If the number of stochastic field is high, we have an agreement with ATF now for the RMS and also for the RMS of Z. Here we have a large discrepancy. And this discrepancy is due to the fact that in this, we have these pilot flames, and we didn't account for the heat transfer at this area, so that this can modify largely the prediction of the prediction of the temperature. So these are what I would like to show to account for the interaction between flame and turbulence first, and also flame with droplets. First, it was in the ATF where we count for this effect. And for this effect, we have modified the, let's come again back. We have modified the transport of the particle temperature and of the mass of the particle. We modify it to get the effect of thickening on this prediction. So there is also some results I will show you tomorrow, in which we account exactly for the way how we introduce the droplets within this thickened area, because if it is orthogonal or if it is parallel to the flame, so we will get some different results. But this result is, I think, it is the realistic one if we account for the inhomogeneities and also different orientation of droplets. For single droplets, we may have a difference, but not for the spray itself. So the other point was to show how we can now include not only the effect of flame on the particles or of the particle on the flame by this way, but how we can remove all these assumptions. Assumption of ATF, this means that we thicken the flame, and assumption on the presumed PDF, where we have this restriction on the physics which take place within the flame. And this was made by this PDF approach, in which we introduce the effect of the mass evaporation in this stochastic field modeling, and we see the results try to be better, and we have to make it in more in many applications, in many to validate it in many applications. So tomorrow I would like to go to the Eulerian methodology, and for that, and also to introduce the effect of that we need the entropy, which is not really well widely used in the community, how to use the entropy evaluation, particularly the entropy prediction, to evaluate the irreversibilities in the system, and also to evaluate the in order to optimize some processes in our system, and how to control the system itself, and also how to modify the system. And this will be done tomorrow. I think I have only some units. I cannot start with this today. I remember only the fact that we have to account correctly, in a correctly way, for the source terms. And I would like to show, I think I have this here, how we have to track the particle correctly. If, let me see this in this way. First, no, it is not here. So how we have to, it is a solution of the exercise I gave you yesterday. I think I will find it. It is not in this transparency. So let me get it in that way. Excuse me. I will get it in a few minutes, I think. So it is here. But let me introduce this slide here now. I think you see it. So let me now make a summary of this coupling. It is in German, but it is not a problem. What I have shown you yesterday was this part here. This part in which we have to calculate first the Eulerian part and then to put in Lagrangian in order to have the source terms, and then we carry out the Eulerian part and then the Lagrangian, and if necessary, we do this loop and we use some under relaxation to get the outcome, so the convergence. So the idea was to track the particle in this Lagrangian way. And here we have our particles. We have the particle, we have to track it within this profile, within this area. And it is there, where we have to get the profile. So we have now, we use the number of real particle in parcels and the mass flow. And here we have the surface, the time, and we have the flux. And the expression we have to do is to estimate the position of the spread of the particle, is to get its position there and to put the correction, which is obtained by this quantity, which account for also for the standard for this correlation we had. And if we have for the velocity, we will have the same, but here we introduce a variance. So the idea is the following here: how to calculate these quantities. We have first the particle volume, the volume fraction. So we have this number of of the volume here of our control volume. We have our time step, and we have the number of real particle in parcels. We have this ratio of time, this delta T to the time taken to try to cross the control volume, and we have the reference time. And the velocity also will be calculated in the same way, and the variance will be obtained also in the same way. So we have the weight. It is given by this number of real particle in our control volume. We have this factor here. We multiply by this, and the particle mass flow will be obtained by getting this quantity multiplied by the density of the particle multiplied by this quantity. Now that is the way we get the different quantities in our simulations. And let me now go to what I would like also to show you yesterday. It is these Eulerian correlations. So we know that we have a cross correlation and length correlation. So this length correlation is the G, and the F is our, the cross correlation is G, and F is the length correlation. I will come now to what I would like to show. No, I think you have no chance to get it today. Oh. It should be before. It should be the solution. It is here. Oh, exactly. Okay. So yesterday I said that we have to find the solution of, yes, we have to find the solution of this motion of a question when we consider the okay. So where we consider only here the drag force and A replace all the other forces. Okay. And the question yesterday I gave you as exercise how to find the velocity and the position of this particle. To solve it, so we consider that this quantity here include all other forces except this drag force. This can be solved for constant velocity of the flow and for constant, this force is constant, and we say that the relaxation time is also constant. Then we solve this, we put dt here and we integrate between two times. So this the time step n and time step n plus 1, and we will get this solution. This is the solution of the exercise. We will get this solution here. So UN plus 1 is equal to this quantity plus where we have this time step divided by this one, and also for these other forces we have there. And to get the position, we have to introduce this expression here, and we integrate between these two time steps. And if we integrate them, we will get this expression here. We have the position at the time step n plus 1 is dependent on the position on the time step, previous time step. And we have the first part, this first part here, plus this also, and plus this term multiplied by this term. And this give us the position of our particle in a time step, having in mind the position in the previous time step. And this means if we want now to calculate the new position, we have the hold position multiplied by this, give us the advancement, and this is the relative velocity multiplied by this. It is this expression. I write it in another way, and we get exactly this here plus this time tau square. And this tau square is this term here when we include this in a correct way. And we obtain this expression plus the other forces. This is what we have put there as A. And the velocity is what also we have obtained. This velocity here is now written in this way, the new one. It is the n+1. It is this one is the time step n, the previous time step multiplied by this, and here is our A. So the time step must fulfill the following criteria. This criteria is this one here. For the time step, this time step must be 0.25 smaller than these 4 time steps. The time to cross the control volume, the integral length scale, the particle relaxation time, and here we have the collision time. Okay, and that is what I put here. The time to cross the control volume, the time, characteristic time for the turbulence, the collision time, and the particle relaxation time. So I will add this tomorrow to this setting of Euler and Lagrangian to show you how we calculate exactly the position and how was the solution of the problem I gave you yesterday to solve. And this is the solution. You can also do it at home and verify the results. So with this, I think I stop here today, and let me answer some questions if you have questions.
Yeah, I mean, participants, if you have questions, you can either raise your hand or type it in the chat box. Yeah, looks there is no question.
Yes. Okay, so I think there is no question.
Yeah, we can then kind of wind up today.